So in this video, we are going to be seeing how classification works. So we are going to be mainly exploring scikit-learn. So I'm using Collab notebook for this particular video. So if you're using a local Jupyter notebook, then you will have to install scikit-learn. You'll have to create a virtual environment and then install scikit-learn. So make sure to check that out on YouTube if you don't know already. So we are going to be starting with classification, and for this particular video we are going to be using the famous MNIST dataset. So for this we are going to be exploring for this video we are going to be exploring the MNIST dataset for digits. So it is going to have digits from 0 to 9, and we are going to be performing classification on top of those images. So this dataset contains images which are 28 by 28 pixels, so around 784 pixels of the total image. So first we are going to be importing the sklearn library, and from the sklearn library we are going to be importing OpenML. From the OpenML we are going to be exploring the MNIST 784 dataset. So I'm just going to be running this as well as I'll be explaining in middle like what a particular thing is and how something works. So after fetching the dataset, now what we're going to do is we are going to basically like pick up the data which is basically the image in X variable, and pick up the target data, which is basically the class of the image in Y variable. And then we are going to be printing one of the images. So this is what a image looks like. So it is basically going to have 784 pixels with or 784 numbers for a particular image in this MNIST dataset. And for each instance we are going to have 784 values, which are going to be numbered from 0 to 255, as the pixel range is 0 to 255, and we are only going to have one channel. So this is going to be black and white images in this MNIST dataset. So this is how it looks like, and then we are going to be printing the Y target for this particular image, which is 5. So for x0 in the dataset we have 5. Now we are going to be visualizing this using matplotlib. So we will have to reshape this 784 uh, uh, image, which is in 784 pixels, into a 28 by 28 pixel 2D array, and for that we are going to use reshape, and then we are also going to plot it using matplotlib. So you can use this inline tool for using matplotlib uh, in a Jupyter notebook or Collab notebook. So this is how it looks like, and then we are going to be seeing the type of this X variable, which is definitely it is a numpy array. So it is a numpy n dimensional array, which we are going to be seeing here. And now what we are going to do is we are going to split this dataset. So as we have already seen, the shape of X, which is basically our data, is 70,000 by 784. So 70,000 is the number of instances or images, and 784 is the number of columns or number of total pixels for a particular image. So we are going to be splitting this dataset. So we are going to use train test split for this. So we are going to import that from sklearn, and we are going to basically use a test split of 0.2. So basically 20% of the data is going to be used for test, while 30% of the data is going to be used for training. And we are going to set a random seed of 42 so that the results are reproducible if we were to run the cells again in the future. So we are going to run this, and then we are going to be seeing the shape or the number of instances uh, that we were able to put in the training dataset. So we have around 56,000 samples out of 70,000 samples originally. So we have 56,000 in training dataset and the remaining 14,000 in the test dataset. And then we are basically going to shuffle, basically just to make sure that there is randomness in the dataset and there is no bias in the dataset. Some algorithms are susceptible to bias or the order of training in the dataset. So we are going to just make sure that we shuffle the dataset before we perform any other operation. So we are going to basically use np.random permutation so that we get uh, get a list numpy array of indices from 0 to 56,000, but they are all randomly shuffled, and then we are going to be obtaining we are going to like pick those randomly shuffled values from the X train and Y train by passing those randomly shuffled indices over here. After that is done, we are going to be using standard scaler. So basically, standard scaler is going to scale the values between 0 to 1. Now we will basically use standard scaler from sklearn preprocessing. Now what fit transform does is it basically calculates the mean and standard deviation. So mean is going to be mean is going to look something like this. Mean is going to be average value, and standard deviation is going to be under root of variation. It is going to be under root of variation. Now once we have this, then this is how we scale using standard scalars. For each example in the training set xi, we basically perform xi minus mean, and this whole value is divided by standard deviation. So by doing this, we make sure that each sample in our dataset is a value between 0 and 1. So, so after that is done, what fit transform basically does is it basically calculates the mean and average uh, for the entire trained dataset, and then mean and standard deviation for the entire X-trained dataset, and then it basically performs the standard scaling on the X-trained dataset, and also performs the same scaling on X-test dataset, because we want to make sure that the same mean and standard deviation is also used on the test dataset, which we have already calculated from X-trained dataset. So fit transform basically transforms this and performs standard scaling operation on this dataset, while it also performs the standard scaling using the same mean and standard deviation values which we obtained from here, and then it performs scaling operation from using those values here as well. So it transforms the X-test dataset as well. Now let's try to train a simple classifier. Now what we're going to be doing for this particular experiment would be for every value which is not 5, we are going to be setting the y variable or the target variable to be 0, and for every sample which is 5, we are going to set the y variable to be 1. So it's going to be a simple binary classifier which is going to classify whether a digit is 5 or not. So we are going to basically set the y variables for both training and testing using this. Now we are going to be training a stochastic gradient classifier. So this basically uses a simple SVM by default if we do not provide a loss parameter here. So by default the loss is hinge, which is the loss function used in SVM. So you can explore more about SVM on YouTube. So this is a SVM classifier by default. Now we are going to be fitting this SVM classifier, or SGD, let's call it SGD classifier, on Xtrain and Ytrain 5. Remember, Ytrain 5 is basically uh, value 1 for samples which are equal to 5, and 0 for all other digits. So for each digit which is 5, the value of y or target is going to be 1, and for the remaining samples or images it is going to be 0. Then we are going to be fitting our classifier on this data set. So we are going to be running this. It is going to basically train the classifier on this data set that we have. So it's going to be a binary classifier which is going to classify either image is 5 or not. Now once it is trained, then we can perform classification on one of the digits. So we can either use the reshape to basically convert this one-dimensional array into two-dimensional array, because for most of the classifiers that sklearn provides, we have to provide data in this format. So the inner square brackets are is actually the the testing example, and the we have to basically enclose it within square brackets, one more set of square brackets. So either we can do this, which is going to be doing the same thing for xtrain 5, or we can use reshape, which also performs this operation. Also, we can either use this xtrain 5, or we can also use this scaled. But it is preferred that we use scaled because we have performed scaling operation at the time of training. Oh, no, sorry. We have to perform scaling operation over here as well at the time of training. Yep. So sorry for that. Let's retrain the classifier. Okay, so it has completed training. Now we are going to perform inference on this scaled example from xtrain. So we obtain the final output as false, which means that the image is not 5. It is some other digit which we can verify by using plt imshow. We have to just run this cell, and maybe we can use this. So as you can see, it is going to basically going to scale down the values from 0 to 255 to 0 to 1. That is why it is looking like this. But if we were to use something like this, basically looking up the original image in the unscaled version, then we are going to be looking at this digit 2. Now we are going to be performing prediction on tested dataset. So what we are going to be doing for that is we are going to perform test detection on test dataset. Now we have the outputs in ypred. Now we are going to be verifying the output against the test dataset, basically the actual ground truth. So we are going to be running this cell. Okay, now so the major caveat is, so as I have already mentioned, that it is only a classifier which is going to be classifying whether a sample is digit 5 or not. So only 10% of the dataset hypothetically contains digit 5, and the rest contains all the digits from 0 to 9 excluding 5. So what this means, if we were to build a simple classifier that just, let's say, returned false, let's say if a classifier always returned false, then we would have gotten the results correct 90% of the times, because 90% of the times the digit is not 5. So we would have accuracy of 90. So this number over here for this classifier, this could mean something, but it doesn't like guarantee that our classifier is going to be performing well on the real world data set. So we will have to use some other measure to classify the efficacy and trustness of our classifier that we have trained. So for that, what we are going to use, we are basically going to use k-fold testing, basically cross validation. So what cross validation is, we basically split the training data set into, let's say, n number of folds. So let's say if our training data set has 10,000 examples, then we are going to, and if the number of folds is 5, then we are going to split the data set into 5 different folds, or 5 different sub data sets, with each sub data set containing 200 examples each. So now what cross validation does is it trains the model on n minus 1 data sets, or sorry, n minus 1 sub data sets. So from the 5 sub data sets, it is going to utilize 4 training data sets for 4 sub data sets for training and the remaining one for prediction. So that is how it is going to train, and then it is going to repeat this process till it has tested over each subset, each sub data set. So this is how cross validation is. Now we are going to run this cell. We are going to basically use this clone function, which we have imported over here. Now what this does is, instead of us having to create a new classifier every time, or initializing a new classifier every time, what this does is it basically clones all those hyperparameters from a given classifier, but it still returns a new classifier. So it basically does not use the fitted weights from a classifier which we are cloning, but just the hyperparameters from that classifier, so that we don't have to initialize or define hyperparameters every time we are running cross validation. So this is what clone does. Now we are going to get the samples from the xtrain variable over here, which are going to be used in the training. So we are going to input those samples in xtrain folds and their corresponding labels in ytrain folds, and we are also going to be using the nth fold, or the fold which is going to be used for testing, and we are going to be taking those samples in xtest fold and their corresponding target variables or target result in here. Now we are going to be fitting this cloned SGD classifier on the xtrain folds with the target variables in ytrain folds, and then we are going to perform prediction on xtest fold, and then we are going to basically compare our result against the actual ground truth, and then we are going to be getting percentages. Here we get 3 percentages because the number of folds were 3, which means that for every, let's say, sub data set, we performed prediction on it at least one time. But that is, we used it as a test data set one time while training the model on the rest of the subsets. So that is why we get 3 percentages over here. After that is done, now we can use cross validation score to get this figure directly. So we can, instead of using stratified k-fold sampling, we can use this function from sklearn model selection cross validation score, and we can get these percentages automatically without writing this code. Now if now the question arises, like, how we can quantify the performance of a model if we don't have the liberty of using accuracy as a metric. What we can do is we can use cross validation predict, and then we are going to be getting the prediction scores. Now please remember, these are the prediction scores, not the actual predictions. So these are not going to be true false values, but the actual scores that the model is going to return. Now when I run this, so we get the prediction scores for each sample in the xtrain dataset, and now we can plot the confusion matrix using the prediction scores that we obtained from this cell, and we can also input ytrain 5, which is the actual ground truth. Now this is going to return a confusion matrix which we can plot over here. So this is basically actual class versus predicted class. So as you can see, we can also print the confusion matrix over here. So this white portion corresponds to this number. So basically the values which were non-5 and they were actually classified as non-5. So you can see the labels over here. This is the actual class and this is the predicted class. So what this column here signifies is the classes, or let's say the numbers which were not 5 and they were correctly classified as non-5. So this is the white portion, which means there is a high density of numbers in this part of the confusion matrix, which can be verified from this number. As you can see, 50,000 is a much bigger number than all these three numbers combined. So this means that most of the non-5 digits were correctly classified as a non-5 by our predictor or classifier. And so this means this column over here is true positive, and this column over here basically signifies the rest of the numbers which were non-5. So basically the numbers which were non-5 but the classifier incorrectly predicted them to be 5. So that number is 481. So there were 481 numbers which were non-5s, but our classifiers had classified them to be 5. So those numbers are 481 over here, and these are basically, so this 50,000 number is true negative, and this over here, this black column which is corresponding to a 1 1, so 1 in the actual class and 1 in the predicted class, this is true positive. 3411, this number is true positive, this number is true negative, and this number is false negative, which means the actual class was 5 but the predicted class was non-5. So this 481 number is, this is false positive because the actual class was non-5 but the predicted class was 5. So this is false positive, sorry. Now moving on, we will learn about precision and recall. So what precision means is basically it is the ratio of true positive to total positive that our classifier has predicted. So total positive is going to be the sum of true positive and false positive, while recall is basically true positive divided by the total actual number of positives that we had in the data set, so which is going to be equal to true positive plus false negative. So these are the two things that are very important. Now to get the precision and recall score, we can use sklearn metrics to import these both these functions, and then we can pass in the actual labels and the predicted labels to obtain precision and recall scores. So we can run this probably. Now if we were to choose, let's say if we have a situation where we have to choose a classifier on the basis of precision and recall, then we will have to calculate the F1 score. So F1 score is basically the harmonic mean of precision and recall, and its value could only be high in case both precision and recall are high. So we can import F1 score from metrics and calculate the F1 score for this particular binary classifier that we have trained. So it can only be high when both precision and recall are high. Remember that.